In this video, we're going to talk about exponential functions word problems. There are many types of word problems that require an exponential function approach. When faced with one of these questions, we can use the equation a equals p times b to the exponent n. A refers to the final amount of the quantity being considered. To help you remember, you might think A stands for after. P refers to the initial amount of the quantity being considered. To help you remember, you might think P stands for previous or prior. B refers to the multiplier, which is the base of the exponent. And N refers to the number of times the multiplier is applied. So if it was a weekly question, N would refer to the number of weeks. In one of these exponential questions, we will typically be given the values to 3 of the 4 variables. One of the most common difficulties that students have is dealing with the value of b, the base. Sometimes we have a half-life question. Scientists keep track of the rate of decay of different substances by using a half-life. A half-life is the length of time that it takes for a given substance to decay to 1/2 of the current amount. So for example, if it takes 1 year for a substance to decay from 500 grams to 250 grams, then the half-life of the substance is 1 year. Since the half-life of a substance is constant, then it will take 1 year for the substance to decay from 250 grams to 125 grams, and 1 more year for the substance to decay to 62.5 grams, i.e. 1/2 of that, etc., etc. In a half-life question, the base of the exponent is 1/2, so in other words, b equals 1/2. Another common exponential function word problem question is a doubling period question. Scientists often use doubling periods to help keep track of rapid population growth, for example, in a population of bacteria. The doubling period is the length of time that it takes a population to double in size. So for example, if it takes a population of bacteria 1 hour to grow from 200 to 400, then the doubling period is 1 hour. It will similarly also take 1 hour for the population of bacteria to double from 400 to 800, 1 more hour to double from 800 to 1600, etc. In a doubling period question, the base of the exponent is 2. In other words, b equals 2. We also have other rate of growth questions. In many questions, we're told the percentage rate of growth over a given period of time. So for example, imagine we're told the value of an item increases by 6% every year. This means that after 1 year, there will be 106% of the original amount. You keep the original 100% and add 6 more percent, you have 106% of what you started. If you had 100% of what you started with, you'd have stayed constant. But since you grew by 6%, you now have 106%. To obtain that value, you would therefore multiply the original amount by 1.06. Percent means divided by 100. Okay, so to obtain the amount after 2 years, you'd multiply the original amount by 1.06 and 1.06 again. In other words, you'd multiply the original amount by 1.06 squared. To obtain the amount after 3 years, you'd multiply the original amount by 1.06, then also by 1.06, then again by 1.06, in other words, 1.06 cubed. In summary, you could let the base be 1.06 and let the exponent n be the number of years. Of course, if we were told the amount increased by 6% each week, then the base would still be 1.06, but the exponent would be the number of weeks. In summary, during examples of exponential growth such as this, the base of the exponent is given by b equals 1 plus rate of increase, with the rate of increase expressed as a decimal. So for example, 5% would be expressed as 0.05, meaning the base would be 1 plus 0.05 equals 1.05. Okay, the multiplier would be 1.05. Another way of thinking of that is if you've increased by 5%, then you've kept 105% of what you originally started with. So you would multiply by 1.05 to determine that. However you choose to think of it is fine. Now, rate of decay questions. In many questions, we're told the percentage rate of decay over a given period of time. So for example, imagine we're told that the value of an item decreases by 3% every year. That means that after 1 year, there would be 97% of the original amount. So if you were told that your bank account decreased by 3%, you would still have 97% of what you started with. In other words, you could take what you originally started with and multiply it by 0.97. Okay, and that's what we're saying here. Now, to obtain the amount after 2 years, you'd multiply the original amount by 0.97 two times, in other words, 0.97 squared. And the amount after 3 years, we'd multiply by 0.97 cubed. So in other words, you could let the base be 0.97 and the exponent n be the number of years. But of course, if you're told the amount decreased 3% each week, then the base would still be 0.97, but the exponent would be the number of weeks, i.e. however many times that base needs to be applied. So in summary, during examples of exponential decay, the base of the exponent is 1 minus the rate of decrease. So for example, if you were decreasing at a rate of 4%, you could say b equals 1 minus 0.04, which would be 0.96. Or another way of saying that would be if you were decreasing by 4%, you'd be keeping 96% of what you originally had. In other words, multiplying by 0.96. However you choose to think of it is fine. So let's do some questions. What if we were told that a ring has a value of $600 today, and the ring increases in value at a rate of 5% per year, and we want to know the value of the ring in 10 years? Well, the $600 is before the rate of growth occurs. So we don't know the after amount, but we do know the prior amount before any of it is 600. Now, B will be 1 plus I. Now, in this case, that 5% is indicating our rate of growth. So it's 1 plus 0.05, which is 1.05. The N will be 10 because the increase is 5% per year, and we're being asked about 10 years from now. So the N value is 10. That 1.05 multiplier needs to be applied 10 times. So A equals P times B to the N becomes A equals 600 times 1.05 to the 10. And using a calculator, that's roughly 977.34. So the value of the ring in 10 years will be approximately $977.34. Now, what if we had a car that had a value of $16,000 today, and the car was to decrease in value at a rate of 14% per year? We want to know the value in 8 years. Well, again, the $16,000 is the prior amount. There hasn't been any decrease yet. The after amount is what we're looking for. Now, the B value will be 1 minus the rate of decay. Now, the rate of decay is 14% per year, so that's 1 minus 0.14, which is 0.86, which actually makes sense. Remember, if we're decreasing 14% each year, then we're keeping 86% each year, meaning we should multiply by 0.86. So there's a logic to that. The N is 8 because this is happening per year, and we want to know the value in 8 years. So we can say A equals P times B to the N. So A equals 16,000, the prior amount, times 0.86, the multiplier, to the exponent 8. And that ultimately equals roughly 4,787.49. So in 8 years, the value of the car will roughly be $4,787.49. Now, what if a particular chemical has a half-life of 60 days, and there are 20,000 grams today? Well, that's the prior amount because they're asking us how much there will be in 300 days. That's the after amount that we don't know. We said earlier that the base of a half-life question will be 1/2. Now, how many times does that base get applied? If a half-life is 60 days and we've had 300 days go by, then 300 divided by 60 is 5, meaning that we've had a total of 5 half-lives. In a half-life question, n is the number of half-lives that have gone by. So A equals P times B to the N becomes A equals 20,000 times 1/2 to the exponent 5, which is 625, and there will be 625 grams of the substance in 300 days. Now, what if we were determining the value of P? So, for instance, suppose a house has been appreciating in value at a rate of 7% per year. Appreciating means increasing. We know the value of the house today is $675,657. We want to know what it was worth 12 years ago. Since we're looking at a past value, today's amount is the after amount, and the P is what we're looking for. Now, B is going to be 1 plus the rate of growth of 0.07. So the B will be 1.07. N will be 12. So we can write this out as A equals P times B to the N. In other words, 675,657 will equal P times 1.07 to the exponent 12. Well, we can divide both sides by 1.07 to the exponent 12, and whatever we get will equal P. And when we do that calculation, P is roughly equal to 300,000. Another way of writing this out is to simply say when we have 1.07 to the exponent 12 in the denominator, we can call it 675,657 times 1.07 to the exponent negative 12. You can make 1.07 to the negative 12 be in the numerator rather than 1.07 to the positive 12 be in the denominator. Either way, that equals the prior amount, which is roughly $300,000. Now, what if a hockey card depreciates at the rate of 9% per week? We know the hockey card will be worth $15 in 20 weeks. We want to know what it's worth now. Well, that would mean that 20 weeks from now is A, so A is $15. P is what it's worth now because that's before 20 weeks from now on a timeline, so P is unknown. The base will be 1 minus that 9% decay rate, so 1 minus 0.09 is 0.91. N is equal to 20. So A equals P times B to the N becomes 15.00 equals P times 0.91 to the 20. And ultimately, P equals approximately 98.92. So the hockey card's worth approximately $98.92 now. Now, what if we're looking to determine the value of B? In other words, we know the values of A and P and N. In these sorts of questions, we want to isolate B to the N and then find the nth root of both sides, or equivalently raise each side to the exponent 1 over N. So for example, if an investment firm grew from a value of $300 to a value of $800 in 20 years, we'd want to know an investment grew, sorry, not an investment firm. We want to know the average annual rate of increase. So the initial amount was 300 and the final amount was 800. So P is 300, A is 800. We want to know the annual rate of increase. So that means per year. So N will be the number of years, which in this case is 20. But we don't know what B equals. So A equals P times B to the N means 800 equals 300 B to the 20. We can divide each side by 300 and we get this expression here. 800 over 300 equals B to the 20. Well, what you can then do, you can take two different approaches to this. You can say, I'm going to raise 800 over 300 to the exponent 1/20th, and I'll raise B to the 20 to the exponent 1/20th. Then 20 times 1 over 20 will be 1. So 800 over 300 to the exponent 1/20th will equal B to the exponent 1. B to the exponent 1 is the same as B. And so I just use my calculator to figure out 800 over 300 to the 1/20th. Or alternatively, we can do what we actually did in the typewritten portion. We can simply raise the left-hand side, which is 800 over 300, to the 20th root. So get the 20th root of that. We already know the 20th root of B to the 20 will be B. Either way we do it, we end up with B equaling approximately 1.050. Okay, well, this question is asking for the average annual rate of increase. We know B is equal to 1 plus the rate of increase in one of these questions. So in other words, subtracting 1 from each side, we see B minus 1 equals the rate of increase. Well, if B is 1.050, then 1.050 minus 1 will be the rate of increase. So the rate of increase is 0.050. But remember, we're expressing that as a decimal, not as a percent. So to express it as a percent, we multiply by 100 and get 5.0. So that 0.50 in that part of the question relates to a rate of growth of 5.0% approximately per year. Now, what if a value of a house decreased from $900,000 to $700,000 over a 10-year span? Well, that would mean the final amount was 700,000 while the initial amount was 900,000. But we don't know what the base is, but we know that 10 years have gone by and we're being asked for the annual rate of decrease, which means per year. So if A equals P times B to the n, then we can say 700,000 equals 900,000 times B to the exponent 10. Dividing both sides by 900,000, we get this expression right here. We can then do one of two things. Either take the 10th root of the left and say that that equals B, and B is roughly 0.975. Or if we prefer, we can simply say the left-hand side was 700,000 over 900,000, and the right-hand side was B to the 10. We can raise the left-hand side to the exponent 1/10, raise the right-hand side to the exponent 1/10. This value right here, according to our calculators, will be roughly 0.975, and B to the 10th to the 1/10, when we multiply those exponents, we'll get B to the 1, which is the same as B. So B will be roughly 0.975. Now, since B is equal to 1 minus the rate of decrease, then we can simply say that the rate of decrease will be equal to 1 minus B. So 1 minus 0.975 will be equal to 0.025, and moving that decimal spot over 2 spaces, we see that that translates to a 2.5% rate of decrease. Now, what if we're looking for the value of n? In other words, we already know the values of a, p, and b. To answer these sorts of questions, we need first a lesson in logarithms. A logarithmic equation is the inverse of an exponential equation. So for example, since 2 to the 3 equals 8, we can say that the log base 2 of 8 equals 3. The base of the exponent is 2, and that's the base of the logarithm. The exponent itself is the answer we're looking for. Okay? So we use logarithms when we're trying to determine the value of a variable that's in an exponent, and there's literally no substitute for memorizing this sentence. That's a definition. You have to know that definition. So, for example, if we said 1.05 to the exponent n was equal to 1.885649, to figure that out mentally would take quite a while, but we could simply instead say n, the exponent, is equal to the log base 1.05, base of the exponent, of 1.885649. We plug that into a calculator and we see n is approximately equal to 13. So it's pretty useful to have logarithms. So that log button on your calculator is pretty useful. However, not all calculators can handle logarithms of any base. Many calculators only have a log button. If you see a log button with no base indicated, the base is assumed to be 10. So I'm going to show you something really useful if you have such a calculator, but before I do, I'll just explain to you what log base 10 means. If you wanted to know the log of 1,000, if you had a log button on your calculator and you just determine the log of 1,000, what you would get is the answer 3. The reason is, if you see log without a base, the base is assumed to be 10. The log base 10 of 1,000 equals 3 because the base of the logarithm becomes the base of the exponent. The answer is the exponent, and we all know that 10 to the 3, in fact, does equal 1,000. Okay? Now, so here's a useful rule. If I wanted to know the log base a of b, but I didn't have a calculator that could do log base a, what I could do instead is just say that the log base a of b is equal to log b over log a. So go back to the question we just did a couple of minutes ago. We said 1.05 to the exponent n equals 1.885649. Now, it would be great if you had a calculator that could answer for you the log base 1.05 of a number. But many calculators can't do that for you. So if you have a calculator that can't give you a random base like 1.05 for your logarithm, then instead what you do is simply use the log base 10 of 1.885649 and put it over the log base 10 of 1.05. Now, when you're in grade 12 advanced functions, you'll learn a few rules of logarithms and you'll understand why this works the way it does. For now, it might be just you have to take my word for it. But one thing I used to do to remember this before I learned more rules about logarithms was I remembered that the base of the logarithm, if I'm using a calculator that can't handle any base, then the base of the logarithm, 1.05, goes in the basement of the fraction. So again, if I'm doing the log base 1.05 of 1.885649, and I have a very average calculator that can't handle logs of any bases, it just has a log button, then what I can do is I can say, okay, the base of the logarithm is 1.05. That'll go in the basement of my fraction. And the other number there will go in the numerator, and I'll make it log 1.885649 over log 1.05. Okay, and I memorized that, and then I knew if I plugged that into my calculator correctly, the answer was 13. Okay, so here come three relatively straightforward logs questions, followed by one more trick question where we kick it up a notch. Suppose a house appreciates at a rate of 5% per year. The house is worth $100,000 today, and we'd like to know how long it'll take the house to be worth $188,565. Well, A is $188,565. That's the final amount, the after amount. P is 100,000. That's the prior amount because today is before many years from now when it's worth 188,565. So the prior is 100,000. The after is 188,000. The base is 1.05 because it's 1 plus the rate of increase. 5% changes to 0.05. So we get a base of 1.05. And n is unknown. So we can say A equals P times B to the n. So 188,565 equals 100,000 times 1.05 to the n. Dividing both sides by 100,000, we get 188,565 over 100,000 equals 1.05 to the n. Then what we can do is we can say that that exponent of n can be solved using logarithms. The log base 1.05, the base of the exponent is the base of the logarithm of 188,565 over 1,000. If you have a calculator where you can press it in just like that, that's great. But if your calculator can't handle that, then all you do is you do the log of 188,565 over 100,000 over the log of 1.05, because the base of that, if you're using the more average calculator way of doing things, then the base of the exponent, the base of the logarithm goes in the basement of the fraction, so that log 1.05 goes down there. So if you have a more average calculator, you'll do this calculation. If you have a fancier calculator, you'll do this one. But either way, you get an n value of approximately 13. And we can say, therefore, it'll take about 13 years for the house to appreciate in value to $188,565. Now, what if a city's population is decreasing at a rate of 4.2% per year? So if the population of the city is 62,217, how long will it take for the population to be 30,000? Well, this is the prior amount, and this is the after amount. So A is 30,000, P is 62,217. It's decreasing, so I'm going to go 1 minus that 4.2%, but I move that decimal spot over 2 places, and it's 0.958. And n is unknown. So A equals P times B to the n. I plug my numbers in. I divide both sides by 62,217, and I get this equation here. And I can simplify that to this expression at the bottom. N equals log base 0.958 of 30,000 over 62,217. If you have a pretty fancy calculator, you can do that equation I just starred. If you don't, then what you can do is just determine the log of 30,000 over 62,217 and divide that by the log of 0.958. The reason that works will be explained to you in grade 12, as we mentioned. But for now, we can say either way, n is equal to 17. And since it's measured in years, we can say it'll take about 17 years for the city's population to decrease to 30,000. Now, what if we have a substance with a half-life of 325 days, and we want to know how long it'll take for 9,000 grams to reduce to 1,500 grams? Well, the final amount is 1,500 and the initial amount is 9,000. The base is 1/2 and n is unknown. We can say A equals P times B to the n, so 1,500 equals 9,000 times 1/2 to the exponent n. Dividing both sides by 9,000, we get 1,500 over 9,000 equals 1/2 to the n. So n will ultimately equal the log base 1/2 of 1,500 over 9,000. Fancy calculator, you can press that straight in. A not so fancy calculator, you can simply say it'll be the log of 1,500 over 9,000 divided by the log of 1/2. Either way you do it, you'll get that n is roughly 2.5850. Now, what that means is there have been roughly 2.5850 half-lives that have gone by. Okay, now one half-life is roughly 325 days. So we have 2.5850 half-lives times 325 days in a half-life. When you multiply that out, it's roughly 840 days. And we can say it'll take approximately 840 days for that drama to conclude. And finally, our kick it up a notch question. There are 300 grams of mathium today, but we know there were 50,000 grams of mathium 80 days ago. We want to know the half-life of mathium. And we want you to round the answer to the nearest minute and express the answer in days, hours, and minutes. So the final amount is 300. That's how much there was today. The initial amount is 50,000 because that's what there was earlier, 80 days ago. We know anytime it's a half-life question, B is 1/2, but we don't know what n equals. So we set up our equation. That's always helpful. Divide each side by 50,000 and come up with this expression for n. N is the log base 1/2 of 300 over 50,000. Now we can evaluate that two ways. If we have a calculator that's pretty fancy that can handle log base 1/2, we can simply press those numbers in like that. And n is roughly 7.3808218. If we have a cheaper calculator that doesn't quite do that, then we can simply say it's the log of 300 over 50,000 divided by the log of 1/2, which again is roughly 7.3808218. And just one more time, in case it got lost on you, the way you can tell if you can do this is if you have a button that's something like log with a optional base, or maybe it's the log base X, and there's like an optional base for you. But a lot of calculators don't have that, and they simply have a button that says log. If you simply have a button that says log, you're doing it this way. Okay, now we want to round to the nearest minute, so I'm using a bunch of decimal places. Now we know n is roughly 7.3808218. Now the total amount of days gone by was 80. So that means 80 days is roughly equal to 7.3808218 half-lives. If it's a half-life question, n is the number of half-lives. We just determined that n is 7.3808218 approximately. That's how many half-lives have gone by. So 80 days is roughly equal to that many half-lives. The question says how much is one half-life? So let's divide each side by 7.3808218. If we do that, we do 80 days divided by 7.3808218. What you get is 10.838901. That's how many days are in one half-life. Okay? Well, that's like saying 10 days plus 0.838901 days. That's what 10.838901 days means. 10 days plus 0.838901 days. Well, 0.838901 days is less than 1, so we're going to have to start expressing that in hours and minutes. We know there's 24 hours in a day, so 0.838901 days times 24 hours in a day equals roughly 20.134 hours. So what we know is there have been 10 days plus 0.838901 days. But we just said 0.838901 days is 20.134 hours. So we know our final answer is going to be 10 days and 20 hours plus whatever 0.134 hours works out to in minutes. Well, 0.134 hours multiplied by 60 minutes in an hour is roughly 8 minutes. So we can say the half-life is roughly 10 days, 20 hours, and 8 minutes.